All right, this is section 1-6. We are going to be looking at absolute value functions and some inequalities as well. So first, we're going to talk about solving absolute value equations. In this section, we're going to want to get the absolute value by itself. We're going to write two equations, and the first equation, all we're going to do is remove the absolute value and then solve. In the second equation, we're going to remove the absolute value and multiply the side that didn't have absolute value by -1. And then we want to check our answer because sometimes some strange things can happen and what we get doesn't actually work. So in this first example, I want to get the absolute value by itself. So I'm going to subtract 3 from both sides. I have 2 times absolute value of x minus 3 is equal to 10. This 2 cannot be distributed in. I have to divide it off of this side. So then I have x minus 3 in the absolute value equals 5. And now I can write my two equations. X minus 3 is equal to 5, just removing the absolute value. And the other equation, x minus 3, and then this side we're multiplying by -1, so that'll become -5. And adding 3 to both sides, I get x is equal to 8. And adding 3 to both sides, x is equal to -2. Now, the reason why we do this in solving and trying to get two different equations is if I have the absolute value of x is equal to, let's say, 4. The values I can plug in here are +4. Absolute value of 4 is 4. But I can also plug in -4. The absolute value of -4 is also 4. Absolute value, by definition, is just the distance from 0. And so if you think of a number line, -4 and 4 are the same distance. These are the same size pieces here, the same distance from 0. So the reason we write two different equations is because we're trying to find, well, what x values are going to give me the answer to this that gives me something in here that's equal to 5, but also equal to -5. X minus 3 is equal to 5, but it could also equal -5, and the absolute value of -5 would be 5. So we always want to check our answers, and if I plug in 8, 8 minus 3 is 5. The absolute value of 5 is 5. 5 times 2 is 10, plus 3 is 13. That one does work out. -2. -2 minus 3 is -5. The absolute value of -5 is 5. 5 times 2 is 10, plus 3 is 13, and that does work as well. In the next example, we're going to see something interesting happen. Here, I'm going to go ahead and get the absolute value by itself. So I subtract 6 from both sides, and I get absolute value of x plus 1 is equal to -4. Now, at this point, this should give you some pause because you're seeing here that the absolute value is equal to -4, and I have the absolute value by itself here. Now, by definition, a distance can't be negative. I can't say from here to my front door is 20 feet or is -20 feet. That doesn't make sense. Distances are always measured in positive values. So this should tell me that there's nothing I can plug in here for x that when I take the absolute value of it will give me -4. So right now, I already know the answer to this is no solution. There's nothing that I could plug in. However, let's say you just didn't notice it. You're just kind of on autopilot, not really thinking through it. And you said, okay, well, let me go ahead and write my two equations. I have x plus 1 is equal to -4, just removing the absolute value. And then x plus 1 is equal to multiplying by -1 on this side, +4. And you were like, well, let me go ahead and plug those in and check those values. So you subtract 1 and you get x is equal to -5. And you subtract 1 and you get x is equal to 3. And you plug those in. Let's start with -5. -5 plus 1 is -4. Absolute value of -4 is 4. 4 plus 6 is 10. Well, 10 is not equal to 2, so that one does not work. And I can plug in 3. 3 plus 1 is 4. Absolute value of 4 is 4. 4 plus 6 is 10. That is not equal to 2. So that one doesn't work. And so we still come back to the same conclusion of no solution. Let's take a look at the graph of absolute value of x. We've seen this in a few sections now where we are looking at the parent graph of absolute value of x. We've done some shifting of it, but let's just kind of see the behavior of it. Let's plug in -3, -1, 0, 1, and 3. And I'm picking these values. You get to pick your x values, and I just want to get a good spread of points here to see what the graph looks like. So when I plug in -3, the absolute value of -3 is 3. That's the distance from 0. Plugging in -1, we get 1. Plugging in 0, well, the distance from 0 of 0 is 0. It's on 0 already. Plugging in 1, we get 1 and 3. So -3, 3, -1, 1, 0, 0, 1, and 3, 3. And we get these sharp lines here. Excuse me. And that is the graph of our absolute value function. We saw in a previous section how to shift our graphs. This -4 on the inside, we'll shift it to the right 4, and this +2 on the end, we'll shift it up 2. So that same absolute value graph that we just saw, if you wanted to put a couple of dots here and use that to help you, then all of those are going to be moved up 2 and right 1, 2, 3, 4. Up 2 and right 1, 2, 3, 4. Up 2 and right 1, 2, 3, 4. And I can continue moving those and drawing my graph. And that is f of x. In the next example, we have a few different shifts here. What I'm actually going to do is use the parent graph where I have x and then y equals -1/2 absolute value of x. And I'm going to choose x values that are divisible by 2 because I don't want to deal with fractions. So if I pick things that are divisible by 2, then my fraction will cancel out here. So I'm going to choose -4, 0, and 4. And so I have -4. Absolute value of -4 is 4. 4 times -1/2 is -2. 4, absolute value of 4 is 4, times -1/2 is -2. 0, 0, absolute value of 0 is 0, times -1/2 is 0. So I have these points I can go ahead and plot. 0, 0, -4 and 2, and +4 and 2. But I have these shifts. I have this left 6 and down 1. So left 6, 1, 2, 3, 4, 5, 6, and down 1. Left 6, 1, 2, 3, 4, 5, 6, down 1. Left 1, 2, 3, 4, 5, 6, and down 1. And I can go ahead and draw my graph f of x. Okay. Now, the next part of this section is looking at compound inequalities. And we saw these in a previous section as well, but we're going to give a little bit more detail to them. We did talk about and or inequalities, but I've written it out here for you. So and inequalities is where they're both shaded. This was that overlapping area we saw. Or inequalities are where we kind of combined the graphs. It just had to be one or the other. So we're going to go ahead and solve these and graph them. Actually, they're already solved for us. We're just going to go ahead and write out those graphs. This is an and inequality. So let's see. I have -1 and it's an open dot and x bigger than that. And then I have x is less than or equal to, so closed dot, 3 and everything less than that. And I want this overlapping area because we want where it satisfies both of them, those and inequalities where both are satisfied. So my answer is one number line here, -1, 3, closed dot, open dot, and it's where they're both shaded. And then writing that in interval notation would be -1, 2, 3, and then a bracket on 3. Now, if we're looking at an or inequality, and we have, let's see, -1 and 3, close dot here, x greater than 3, and then x less than -1. And it just has to satisfy one or the other. So my answer, it just has to be either here or here. It does not have to be both. This would be -1, 3, close dot, open dot, this here and this here. And it's going to take me two intervals here to list this out because I have two shaded areas. So let's get into some examples or an example. We're going to see how this will play out here in this absolute value inequalities example here. Now, sometimes you'll see absolute value inequalities. We saw one in a previous section, but this chart here is really helpful in distinguishing what categories kind of these are in. So if you have a less than or equal to absolute value inequality, this is going to behave like an and inequality. If you have a greater than or equal to, where the absolute value is greater than or equal to, you're going to have an or inequality. So let's see how this gets set up in this example here. So first I need to get the absolute value by itself. So I subtract 1 from both sides, -2 absolute value 3x minus 5, and less than -16. I can divide both sides by -2. But remember, when we have an inequality, if we divide both sides by a negative number, we have to flip the direction of the inequality. So now it's pointing this way, and that'll be +8. And now I can go ahead and write two inequalities, but notice it's pointing to the absolute value. So using my chart up here, it is going to behave like an or inequality. We actually have this scenario here. So I have 3x minus 5 is greater than 8, or I have 3x minus 5 is less than -8. And again, it's an or inequality. So I can go ahead and solve both of these. +5, +5, 3x is greater than 13. X is greater than 13 over 3. +5, +5, 3x is less than -3. X is less than -1. And I can go ahead and look at those graphs kind of lined up with one another. I have 13 over 3 and -1. Open dot for both of those. Here, x is greater than this value, so we're shading to the right. Here, x is less than this value, so we're shading to the left. It is an or inequality, so it just has to satisfy this or this. So my answer then is going to be -1, 13 over 3, open dot on both. It just has to be one or the other. It doesn't have to be both. So there's not worrying about the overlapping area. You're essentially just squishing those graphs together. And that is our answer. And that is the end of this section.